Hi, my name is Julia and I'm going to be teaching you chapter 1.5 in your math book. This chapter is about prime and composite numbers as well as testing for divisibility. First, I'm going to explain to you what a prime and composite number are. A prime number is a number that has factors only of 1 in itself. A composite number has 2 or more factors. Now I'm going to teach you how to determine a number's factors. You use a factor tree, which determines if a number is prime or composite. What is a factor tree? A factor tree is when you divide a number until you have a set of prime numbers that can be multiplied to get the original number. Here are some examples of factor trees. 7 times 1 equals 7. This is the only way to break down the number 7 in whole numbers. This means that this is a prime number. 19. 19 also cannot be broken down any way besides 1 times itself, which is 19, meaning this is a prime number. Now we have 12. This is 3 and 4. However, 4 is not a prime number. This means you can break it down farther. So 2 times 2 times 3 is more than 2 factors, and besides 1 in itself, which means it's a composite number. Here we have 21. Which is 3 and 7. 3 and 7 are both prime numbers. However, this factorization is not 1 in itself, making this a composite number. Now I'm going to teach you the fundamental theorem of arithmetic. This says that each composite number can be shown by a series of prime numbers whose sum is that of the original composite number. Here I have 2 examples of how this is done. First, you need to make a factor tree. I chose 75. For 75, you can break it down 5 times 15. Since 15 is composite, you break that down 3 and 5. Then you make a list. 5 times 3 times 5. Next step, order and convert. So you have 3 and 5 squared. Since you have 2 5s up here, you need to make it 1 5 and square the number. If there were 3 5s, this would be 5 to the third. Another example I use 28. 2 times 14. 14 can be broken down to 2 and 7. You make your list, 2 to 7, order and convert. 2 to the second times 7. Now I'm going to teach you the definition of divides. This stands when you let a and b be any whole number besides 0. You write divides as a/b. To write an unequal equation, you write a, the line with a dash through it, b, meaning a does not divide by b. One way to do this is by making a dot chart. In a dot chart, you can let a equal the number of rows and b equal the number of dots. Here, I also have 2 examples. 3 divided by 12. Here, we have our rows, which are 3. I've also numbered each of these so you can see that there are 12 dots. Since all these rows are completely filled out, you can see that yes, it divides because the rows were completely filled. Next, we have 5 divided by 12. As you can see, I have 5 rows, but this column is not completely filled out. This means no, they do not divide because you are missing 3 here. Now I'm going to teach you some divisibility rules. These are rules which can be applied when working with big numbers, so you don't have to go through any long division math to figure out your answers. Our first rule is the divisibility of 2, 5, and 10. In this rule, you look at the ones place as the determinator on if it is divisible by these numbers. Here I have several examples. Our first example is 7,486. Here, you look in the ones place, which is 6. 2 is divisible by 6. This means that, yes, this whole number, 7,486, is divisible by 2. Next, we have 920. Since this is a 0, it means that the number is divided by 2, 5, and 10. All of these places mean it's divisible by all of them. The 0 means 5 and 10, always. 685. Here we have the 5, which means its whole number is divisible by 5. 7,644. 2 is divisible by 4, meaning this number is divisible by 2. Next, I will teach you the divisibility of 3 and 9. For 3, the sum must be divisible by 3. For 9, the sum must be divisible by both 3 and 9. We're going to start off with divisible by 3. First number is 267. 2 plus 6 plus 7 is 15. 3 divided by 15 is 5. Meaning this whole number, 267, is just divisible by 3. I'm sorry, the answer is 5, so the whole number is divisible by 3. 1,687. This means you add 1 plus 6 plus 8 plus 9 equals 24. 3 divided by 24 is an even 8, meaning yes, this is divisible by 3. 1,269. Once again, you add all the numbers up. 3 divided by 16 is not a whole number. It gives you 5.3. This means that 1,269 is not divisible by 3. Next, we're going to do nines. So remember, for nines, you have to divide by both 3 and 9 to determine if it actually works. So first off, we have 153. Once again, you add all the numbers. 1 plus 5 plus 3. 9 divided by 9 is 1, so that works. And 3 divided by 9 also works, meaning 153 is divisible by 9. Our next number is 1,089. You add 1 plus 8 plus 9. You can write the 0 in if you need to, but it does not change your answer. And you have 9 divided by 18 gives you an even 2, meaning it's divisible by 9, but you still have to check for 3. 3 divided by 18 is 6, meaning 1,089 is divisible by 9. Our last is 883. Here we have 8 plus 8 plus 3 equals 19. So you can see up here and down here that's not divisible by either. 9 divided by 19 is 2.1 repeating, and 3 divided by 19 is 6.3 repeating. This means that this number is not divisible by 9. Even if it was divisible, the added number was divisible by 9, and it was still not divisible by 3, that means it is not divisible by 9, the whole number. Next, I'm going to teach you about the divisibility of 4 and 8. For 4, the last 2 digits need to be divided by 4, and for 8, the last 3 digits need to be divisible by 8. Starting off with 4, you have 7,328. Looking at the last 2 digits, you see 4 divided by 8 equals 7, meaning this number is divisible by 4. 19,713. You'd look at the 13. 4 divided by 13 is 3.25. Since it's not a whole number, 19,713 is not divisible by 4. 59,604. You look at the 0, 4. Here, since it's a 0, you just take that off, making it 4 divided by 4, which equals 1, which means the number is divisible by 4. Now, let's try for 8. 9,456. This time, you're going to take the last 3 numbers. So you have 8 divided by 456, 57. Check, it works. This whole number is divisible by 8. Next, we have 79,800, 4,088. So here, since you have 088, you drop the 0, make it 8 divided by 88, 11. Yes, this number is divisible by 8. At the end, we have 79,249. 8 divided by 249 gives you a decimal 31.125, meaning this number is not divisible by 8. Here we have divisibility by 6. For this one, you need to follow the rules for both 2 and 3. Remember, for divisible by 2, the last number has to be divisible by 2, and for 3, the sum must be divisible by 3. Here we have 3 examples. 840. As you can see, 840 ends in a 0, meaning, yes, it's divisible by 2. And then you have to check for rule 3, 8 plus 4 plus 0, 12, 3 divided by 12 is 4, meaning, yes, this number, 840, is divisible by 6. After that, you have 5,790. We look for the 2 rule. It's a 0 once again, meaning, yes, it's divisible by 2. The 3 rule we have is 5 plus 7 plus 9 plus 0, 21. 3 divided by 21 is 7. Yes, this number is divisible by 6. 178. The 2 rule is if the last number is divisible by 2, we have 8, meaning the number 8 and 2 divided by 8 is 4, so this works. And the 3 root 1 plus 7 plus 8 is 16. However, 3 divided by 16 gives us a decimal, 5.3, meaning 178 is not divisible by 6. Next, we have divisibility for the number 11. This means that the sum of the difference of all of the odd place numbers and all of the even place numbers is 0 or divisible by 11. Here we have 10,395. In black, I have written out the odd numbers, the odd place numbers. So this would be the first place, second, third. And then these are the even place numbers. So you add the odd ones, 1, 3, and 5, minus 0 plus 9. You do your parentheses first, giving you 9 minus 9 and 0. Since 0 is one of our options, 10,395 is divisible by 11. Our next number is 6,293. The 6 and the 9 are the odd place numbers, and the 2 and the 3 are the even place numbers. Do the parentheses, giving you 15 minus 6. Then you have 9 minus 11. This gives you 0.81. This is not an even number. It means this number is not divisible by 11. On our last one, we have 909,381. Our odd place numbers are 9, 9, and 8. Our even place are 0, 3, and 1. 9 plus 9 plus 8 minus 0 plus 3 plus 1. Do your parentheses. 25 minus 4. 11 divided by 22 is 2. So this number is divisible by 11. Now I have some theorems to teach you. This theorem says that if you let a, m, n, and k be numbers that aren't 0, then a divided by m and a divided by n, if this is true, then a divided by m plus n will also be true. Here's our example of that. We let a equal 3, m equal 9, and n equal 6. So first we had to have a divided by m be true, 3 divided by 9, true. Then we have to have a divided by n be true, which is 3 divided by 6, which is true. This means that 3 divided by 6 plus 9 should be true. Once we do a parentheses, 3 divided by 15, this is 5. This proves that this theorem is true. Next, we have a divided by m plus a plus n. If these are true, then a equals m minus n. We have the same setup here, since the beginning of the problem is the same. A divided by m is true. A divided by n is true. This means that a should be divided by m minus n equally. So 3 divided by 9 minus 3. 9 minus 3 is 3. This means that, yes, it works. However, you have to note that m has to be greater than or equal to n. This is not true. You will end up with a negative number, which will not work for this theorem. Lastly, you have a divided by m. If this is true, then a divided by k times n is true. Same numbers, a equals 3 and m equals 9, but we're going to let k equal 2. If you have 3 divided by 9 and this is true, that means that you have 3 divided by 2 times 9, which equals 2, which equals 18. So 3 divided by 18 is 6, making this true. Our next theorem. The first is a number is divisible by the product, AB, of two non-zero whole numbers. A and B, if it is divisible by both A and B, with only one as the common factor. We have 2 examples for this one as well. 28. We're testing for 7 and 4. 7 is a prime number. It can't be broken down any more than 1 and 7. 4 is a composite number, so we break it down to 2 and 2. Here you see there are no common factors, so this works. Next, we're testing for 6 and 10 with our answer being 30. 6 can be broken down to 2 and 3, and 10 can be broken down to 2 and 5. Here you see we have a common factor of 2 since we see it in both of our prime factorizations. This means that this does not work for our theorem. Lastly, we have the theorem prime factor test. This is the test using prime factors that you can do to simply find the factors of p and n, using the equation p squared is less than or equal to n. Our first number is 327. First, you have 18 squared is 324, 19 squared is 361. So you have the equation 18 squared is less than 324 is less than 19 squared. This means that you can check for prime numbers 1 through 18 to find factorization. You see here that 3 works. 3 plus 2 is 5, plus 7 is 12. 3 divided by 12 is 4, so this fits with our theorem. Lastly, we have 574. We have 23 squared equaling 529 and 24 squared equals 576. This falls in between these two numbers, so 23 squared is less than 574 is less than 24 squared. First thing you need to do is see that you check 1 through 23, since that's the number you have on this side of the less than sign. First, I checked 3. 5 plus 7 plus 4 is 16. However, 3 divided by 16 gives you 5.3 repeating, which is not a whole number, so this number does not work. Next, I checked for 5. I looked in the last place. Seeing that in the ones place is a 4, this is not divisible by 5, so this does not work with our theorem. Lastly, I did 7. 7 divided by 574, it gives us 82. This works with our theorem. Now you know about prime and composite numbers, testing for divisibility, as well as some other important theorems.